One more last quick example for 7.2, dot product, and that is going to be question 10 on page 376 in your textbook. The question says find a vector that is perpendicular to vector u equal to 9, 2. And in the previous example that I did, which was question 8 about the right triangle, if you took note, the vector, there were two vectors that were perpendicular, and the components of the vectors were related to each other in a particular way. So let me just throw that out there and forget about it for a minute. And let's try doing this from first principles. So we'll just let any vector v be v1, v2. And since I want that vector to be perpendicular to u, then I know that I want the dot product of those two vectors to be 0. And so to calculate the dot product of those two vectors, I would just do the first component of u times the first component of v plus second component of u times second component of v equals 0. And so I need to find scalars v1 and v2 such that they satisfy this equation. They make it equal to 0. And so if I play around with my numbers a little bit, what I need is for both products to be the same, but one to be positive and one to be negative. So I can do that by making v1 2, for example, and v2 negative 9. Let's try it. So 9 times 2 plus 2 times negative 9 is in fact 18 minus 18, which is of course 0. I think I still have actually example 8 here. Right. So what I wanted to show you is that over here, when we did AB dot AC and we got 0, and so therefore we knew they were perpendicular, look at how these vectors were related to each other. So we had negative 5, 2, and then we had 2, 5. So the components are switched and one of them, the sign is changed. There's actually a name for that. It's called transposing the components of the vector. And so that's something, language that is used very often in linear algebra in university math. Transpose the vector. And so whenever we want to find, let's take any other vector here, 3, 2, for example, a vector that is perpendicular to a given vector, all we need to do is transpose the components or switch the components and make one of them negative. Does not matter which one is negative. We can verify that. So A dot B here would be negative 6 plus 6, which is 0. If I had made it vector C instead with the 3 negative, then A dot C would be 6 minus 6, which is still 0. And so just switch the components and change the sign of one of them, not both. If you change the sign of both, let's see what happens. If we do vector D and make it negative 2, negative 3, then is A dot D equal to 0? No, because it would be negative 6 minus 6, which is negative 12, not 0.